goal of this video is twofold. First, I want to introduce you to more sophisticated differential equation models of population growth. Next, I want to give you an idea of how insights about these models' predictions can be achieved without going to the trouble of solving the differential equations in general. I want to start the video with the observation that we can model population growth using the linear differential equation du by dt is equal to a constant r times u. We should likely add that at time 0 we expect the population size to be equal to a. Using techniques described in previous videos, we can solve the recursive differential equation model to obtain a new model that captures an explicit relationship between population size u and time t. Doing so, we find that u is equal to e raised to the power r times t, all multiplied by the initial value a. When we rewrite the new model in this way, we see hints of previous models emerge. In particular, what we've written here as e raised to the power r, we might have written as lambda in a previous week's video. In keeping with previous videos, we find that the model makes two basic predictions. When r is less than 0, alternatively when lambda is less than 1, the population size tends from its initial value of a towards 0 over time. By contrast, when r is greater than 0, alternatively when lambda is greater than 1, the population size grows without bound. It was the predictions of the model in this case that we didn't accept, since they're out of step with what our experience tells us actually happens in nature. I promised to revisit this matter, and since we're now in a good position to tackle the problem, we should take care of it. Before we update our model for population growth, I'd like to reframe its problematic features. The new perspective I want to provide relies on the fact that the differential equation on which the model is based is an autonomous differential equation. This means that the differential equation itself does not explicitly depend on the argument of the unknown function, in this case, t. Because our model is based on an autonomous differential equation, we can get some insight into its predictions by sketching du by dt versus u. For our current model, the sketch is pretty straightforward. For the problematic case r is greater than 0, the sketch is just a straight line of positive slope r that also passes through the origin. Moving on, we imagine the population size as being represented by a particle with the ability to move along the u-axis. The direction of this particle's movement is determined by the point on the graph of du by dt that corresponds to the particle's position. If the graph is above the horizontal axis, then the particle is moving to the right. If the graph is below the horizontal axis, the particle is moving to the left. If the graph intersects the horizontal axis, that is to say, if the graph is neither above nor below the axis, then the particle is at rest. In this picture, the graph of du by dt is always above the horizontal axis, so the particle that represents population size is always moving to the right. In other words, the population size is always growing. Of course, we knew that, and so on one hand, this discussion is a bit unnecessary. On the other hand, though, the discussion sets us up nicely to build up to our improved model. Our improved model needs to connect more closely with our intuition about population growth. That intuition tells us that it's reasonable to expect population growth when numbers are low, but it also tells us that such growth can't be maintained indefinitely. We expect that if numbers become too high, the population size might actually shrink. We can look to capture this with a rough sketch of du by dt versus u. Following our intuition, we think the graph should lie above the horizontal axis for small values of u, and below the horizontal axis for larger values of u. Of course, if the graph is going to be continuous, this switch from positive to negative implies that our sketch will cross the axis at one point, say u is equal to k. If we assume that the population is closed to migration, then there can be no growth when u is equal to 0. This means that our sketch should begin at the origin. Keeping all these features in mind, our new model for population growth should be connected to a graph of du by dt versus u that looks something like this. Going back to our analogy, we see that a particle that is placed on the horizontal axis between 0 and k will move to the right, tending to k over time. Movement to the right occurs because the graph is above the horizontal axis in this region. By contrast, a particle placed somewhere to the right of k will move to the left, but will again tend to k over time. Movement to the left in this case because the graph is below the axis in this region. Overall, our rough sketch suggests that we're onto something. It looks like we have the basis of a model that matches our intuition about population growth. It remains, however, to actually turn this into a differential equation. To pull this off, we can observe that the easiest way to generate a graph like the one in our sketch is with a quadratic in u. Basically, a concave down parabola with roots at u is equal to 0 and u is equal to k. A parabola that ticks these boxes is the following one: u times 1 minus u divided by k. We assume that du by dt is proportional to this quadratic expression to get the following differential equation. Again, we use r as the constant of proportionality. I want to point out that this can also be derived using the conservation law approach detailed in previous videos and in the readings. I'll encourage you to review that derivation later. What we have in the bottom right of the screen is a nonlinear differential equation. It's likely not obvious to us yet how to go about solving this equation. However, as we've seen, the sketch above allows us to understand the model's predictions even in the absence of an explicit solution. For the sake of completeness, let me point out that the model's predictions can be organized by referencing the equilibrium states evident from the sketch. These are places like u is equal to k and u is equal to 0, where the sketch intersects the horizontal axis. Notice that because the graph is neither above nor below the axis at an equilibrium, particles that happen to be placed exactly on these points would remain at rest. It's for that reason we sometimes refer to equilibria as steady states. With those landmarks in mind, we can summarize the predictions by saying that the equilibrium u is equal to k is asymptotically stable, meaning that a solution to the differential equation, had we found one, would tend to a value of u is equal to k over time. We would also say that the equilibrium u is equal to 0 is unstable, meaning that any solution to the differential equation found near 0 will tend away from this value over time. You probably noticed that we can diagnose the stability of an equilibrium based on how the graph cuts the horizontal axis at the intersection. If the graph switches from below the axis to above the axis at the equilibrium point, here denoted as u hat, then the equilibrium is unstable. If the graph switches from above the axis to below at the equilibrium point, then the equilibrium is asymptotically stable. In both of these cases, we can rephrase our observations in terms of the slope of the tangent to the graph of du by dt, evaluated at u is equal to u hat. If the slope is positive, then we can say that u hat is unstable. If the slope is negative, then we can say that u hat is asymptotically stable. Now, because we're using derivatives here, we have to add the caveat that we can only be sure that the stability is local, meaning that solutions to the differential equation that are near the equilibrium tend to the equilibrium over time. Generally speaking, this leaves open the possibility that solutions that are far from our equilibrium tend to some other value over time. You could probably imagine other scenarios too, but we'll focus on the unstable or stable situations illustrated on the left. Before wrapping up, I want to replay our investigation of the new population growth model from a different point of view. I want to imagine that we were given the differential equation and asked to summarize the insights it provides. Now, given that we don't know how to solve the differential equation in general at this point, we could start by finding equilibria. Setting the right-hand side of the equation equal to 0, setting u equal to u hat, and solving for u hat shows that we have two equilibria. One equilibrium at u hat is equal to 0, and another at u hat is equal to k. If we were satisfied with a local assessment of equilibrium stability, we would proceed by differentiating du by dt with respect to u, then substituting u is equal to u hat. In this case, we would get this expression. Subbing u hat equals 0 into the expression yields a quantity that is strictly greater than 0. Thus, u hat equals 0 is an unstable equilibrium. Subbing u hat equal to k into the derivative gives us a quantity that is strictly less than 0. Thus, u hat is equal to k is locally asymptotically stable. Of course, if we weren't satisfied with a local assessment of stability, we could still investigate the model with a sketch of du by dt versus u and adopt the particle analogy developed earlier in the video. The global perspective provided by this option is appealing, but in more complicated scenarios, it may not be available to us. Some problems are just too complex to admit anything other than local investigations. We're winding down, so let's quickly recap. We began the video by revising a simple model of population growth. The revised model ticked the right boxes, but was based on a nonlinear differential equation. The differential equation was autonomous by design, and we saw that this was advantageous. Although we weren't able to solve the differential equation, the fact that it was autonomous meant that we could gain some qualitative insights into the model's predictions using a sketch of du by dt versus u. Finally, we found that some of the insights could be gained not only by the graph we sketched, but also by looking at the slope of the tangent to the graph evaluated at equilibrium points. When you've mastered the concepts presented in this video, you'll be able to do several things. You'll be able to identify a differential equation as being autonomous, and you'll be able to articulate a definition of an autonomous differential equation on a test or an exam. Next, you'll be able to develop a recursive model of a biological phenomenon based on an autonomous differential equation by arguing from a graph of du by dt versus u, as we did earlier in this video. You'll also be able to make observations about the qualitative behavior of solutions to autonomous differential equations using a sketch of du by dt versus u. That is, do solutions, thought of as particles, tend toward or away from equilibria? In addition, when presented with an autonomous differential equation, you'll easily have the capacity to find equilibria and assess their stability without the use of a sketch. Lastly, you'll look at models of population growth with a critical eye and be able to explain how they might be modified to address weaknesses you find. As always, I'll remind you that this video is just the beginning. Attend your tutorials and try the exercises. Maybe even create exercises of your own and share them with your friends. After all, learning about autonomous differential equations doesn't have to be a completely autonomous affair.